If I can't picture it, I can't understand it. Albert Einstein. Welcome students. Today in this lecture of methods of impulse and momentum, we discuss about oblique collisions. In last lecture, we had discussed about head-on collision. In head-on collision, we developed very important idea, that is coefficient of restitution. It was ratio of impulse of deforming forces during restitution period to that during deforming period. And we know that interaction forces or deforming forces act along the common normal at the point of contact of the colliding bodies. Actually, we have assumed that there are no tensile force, friction is absent. So the concept of restitution E is valid for velocity components along the common normal. And we exploit this idea while analyzing oblique collision. Let us see how we'll analyze the oblique collision. Oblique collision. In an oblique collision, velocity vector of at least one of the bodies does not lie on the line of impact, but mass centers of bodies must lie on the line of impact. This second condition, mass center must lie on the line of impact. It is because of central collision, and it prevents any change in state of rotation. Actually, if mass center of any of the body does not lie on the common center or a line of impact, the state of rotation of that body will change. And that idea we can discuss only after studying rotational motion. As an example, velocity vectors UA and UB immediately before an oblique collision and VA and VB immediately after the collision of two balls A and B of masses MA and MB are shown. You can see here in diagram. These are the velocity vectors before collision, and here is a point of contact. Here we can draw the common normal, say in this way. So the common normal we denote by n-axis and common tangent by t-axis. So these velocity vectors are making some angle with the common normal. So this collision is an oblique collision. Now what we do? We assume velocities after collision, say VA and VB, and show diagram immediately after collision, and these velocities we assume arbitrarily, and again to analyze them, what we do? We resolve these velocities along their t and n component and analyze the collision in t and n components separately. These collisions can easily be analyzed in a Cartesian coordinate system, axis of which coincide with the line of impact, the common normal, at the contact point, and the common tangent. Now we identify these axes as n-axis and t-axis. So you can see here the angle between t and n-axis is 90 degrees, so they can be used as coordinate axis. Actually, using t and n-axis have advantage. This coordinate system provides twofold advantage. What are the advantages? Here if you resolve the velocities along t component and t-axis and n-axis, you can see along t-axis there are no interaction forces, so the momenta of none of the body will change, and hence velocity. So along t-axis, velocities of the bodies will remain unchanged. And if you see along the n-axis, the collision can be treated just like a head-on collision. So first advantage, velocity components along the n-axis can be treated similar to a head-on collision. And second, due to absence of components of interaction forces along the t-axis, momenta and hence velocities of the bodies undergoing collision remain unchanged. So that is biggest advantage. So here in oblique collision, a component T component was introduced and that remains unchanged. For N component, it is just like a head-on collision. So there is nothing new about oblique collision. Analysis is quite simpler. Let us see how we analyze it and what equations we can write. Analysis, analyzing an oblique central collision. Here central collision means mass centers are on the line of collision. Show velocity components along the n and t axis immediately before and immediately after the collision, as shown in the given figure. Here you can see this figure. The velocities are shown. Now we draw the common tangent and common normal. So t-axis and n-axis, and we show their components. So this line will show the t component of velocity of A before collision. So we denote it UAT. And similarly, this from here to here will be the n component. So we denote it by UN. Similarly, we resolve UB into its tangential and normal component. So this will be UBT and this will be UBN. Now we show the similar diagram immediately after the collision. Immediately after the collision, we have assumed these velocities VA and VB arbitrarily. Now we draw the t-axis and n-axis and show their component. So this will be VAT, this will be VAN, again this will be VBT, and this will be VBN. Now, as we have earlier discussed that tangential components of velocities will remain unchanged. So VAT will be equal to UAT and VBT will be equal to UBT. So there is no change regarding tangential component. And for normal components, we can treat the collision just like head-on collision. Components along the t-axis. Friction between the bodies undergoing a collision is assumed to be absent until it is not stated. To consider, in absence of frictional forces, components of interaction forces along the t-axis are absent. Therefore, t components of momenta and velocities of the bodies undergoing collision remain unchanged. So what we can write? VAT is equal to UAT. We call this equation 1. And what we can write? VBT is equal to UBT. Equation number 2. So these two equations we can write, or these two results we can write without any analysis. While solving problem, here we analyze it. Now we are going on what we do for the n components. Components along the n-axis. For components of velocities along the n-axis, the collision can be treated like a head-on collision. In head-on collision, we use two equations. One is the conservation momentum equation and other one is the idea of coefficient of restitution. So the momentum along the n-axis is conserved. What we can write about it? MBVB n component plus MAVA n component is equal to MAUA n component plus MBUB n component. Let us call this equation number 3. Concept of coefficient of restitution. I will again stress that E is defined for n component of velocities only. So what we can write here? VBN minus VAN is equal to E times UAN minus UBN. We call equation number 4. Now, an oblique collision can be analyzed with the help of these 4 equations. Out of these, first 2 are the direct result. And here, 3 and 4 we have to solve similar to an head-on collision. The above 4 independent equations are sufficient to analyze an oblique central collision. Now, what the idea we have developed, we try to implement these ideas in some example problems. Say example 1. Disc A sliding on a frictionless horizontal floor collides with a stationary identical disc B as shown. Here this idea is given. And disc A is moving with velocity 5 meters per second at an angle 37 degree with the x-axis. Here you can see in the diagram, the x-axis is the common normal at the point of contact. So y-axis will be that common tangent. So x-axis here will treat as the n-axis and y-axis will treat as t-axis. And of course, disc B was stationary. What we to find? If collision is perfectly elastic, find velocities of the disc after collision. Actually, this part A I am making too simple just to illustrate the idea that what we will do along the t component and what will we do for the n components. Because for n component it is head-on collision, and head-on collision in perfectly elastic bodies and of equal masses, the bodies exchange their velocities. So again here we will not be involved in any calculation, only just we see how independently we can treat the collision n component and v component of velocities. So how we'll proceed? In the given situation, the x and y axis are n and t axis respectively. So here is the diagram immediately before the collision. So we resolve, that is 5 into t and n components. So before we label x as n and y as t. So now let us resolve 5 into components. So 5 sine 37 is 3 meter per second is the tangential component, and 5 cos 37 equal to 4 meter per second is the normal component. Now we can assume the velocities after collision VA and VB and show their component, find their values. But if we can predict values priorly, then we find value and start showing the component. And we know that the tangential component of ball A will remain same and tangential component of ball B will be 0. So let us first analyze it. Components along the t-axis. The t components of velocities of the bodies remain unchanged. So what we can write about tangential components, that is VAY is equal to 3. VAY is tangential component of velocity of disk A after the collision. And what about disk B? VBY is 0 because before the collision there was no tangential component of velocity of disk B, so it will remain 0. Now we show them here in this diagram. So that is 3 meter per second, tangential component of velocity of disk A. Normal component is pending to decide, and disk B has no tangential component. Now we discuss about normal component of velocities. Components along the n-axis. In a perfectly elastic head-on collision, bodies of equal mass exchange their velocities. Thus, in this collision, the disks exchange their n components and hence the x components of their velocities. So by this idea, what we can write? The n component of velocity of disk A will be 0 because earlier it was for B 0. And n component of disk B will be 4 because it was for A. So here we can write the n component result directly. So what? VAN is equal to UBN. It means VAN or VAX is 0. VBN is equal to UAN. It means UBX is equal to 4 meter per second. Now we show this component here. So the problem is analyzed. Here I have taken this problem specifically just to show that an oblique collision can be analyzed while treating n and t component independently. Here specifically taking equal masses and E equal to 1, there we have to not make an equation and do calculation for the n component, but in next part we do the same thing. Velocities of the disk after the collision we can write here. So VA will be 3j cap meter per second and VB will be 4I cap meter per second. So VA vector is 3j cap meter per second and VB is equal to 4I cap meter per second. In part B, if the coefficient of restitution is 0.5, find velocities of the disk after the impact. Now here in this problem, what we have learned in previous part, that T and N component can be analyzed separately. And this part, coefficient of E has a value greater than that is other than 1. So we had to make momentum conservation equation and coefficient of E equation and analyze how we'll solve along the n-axis. So that situation was given here. Disk A has velocity 5 meter per second at angle 37 degree from the common normal, and y-axis is the common tangent. In the given situation, the x and y-axis are n and t-axis respectively. So how we'll analyze along the t component, because they will remain same. What was earlier, in this case, the t components will remain the same. The t components of velocities remain unchanged. So what we can write here? Vay is equal to 3 meter per second and Vby is equal to 0. What we obtained earlier. So here we draw the diagram immediately before collision and then immediately after collision and show the t components. So that is a t component 3 and n component of velocity of ball A. Now immediately after the collision. So t component of velocity of A is 3 meter per second and there is no t component of velocity of this B. Now we have to solve or analyze what will happen along the n component or n axis. So how we proceed? Vn will assume and similarly Vb and An will assume arbitrarily and we will determine their values. Now for n component or components along the n axis, we write first momentum conservation and then E. For n components, the collision should be treated like a head-on collision. So what we can cite? The momentum along the n axis is conserved. So what we can have? Mb Vbn plus Ma Van is equal to Ma Uan plus Mb Ubn. And substituting the values, what we get? Mb Vbn plus Mvn is equal to M into 4 plus M into 0. Now we cancel out the M from entire equation and what we get? Vbn plus Vn is equal to 4, equation number 1. Coefficient of restitution is defined as Vbn minus Van is equal to E times Uan minus Ubn. Now we substitute the values. So what we get? Vbn minus Vn is equal to 0.5 into Uan was 4 and Ubn was 0, so 4 minus 0. So here we get 2. So the equation is Vbn minus Vn is equal to 2. We call it equation number 2. Now by solving equation number 1 and number 2, we can find Vbn and Vn. From equation 1 and 2, we get Vbn is equal to 3 meter per second and Van is equal to 1 meter per second. Now we can show their values here. So the complete answer we have explored about the problem. Velocities of the disk after the collision. Now we can write, because we know that the n-axis is the x-axis and t-axis is the y-axis. So we can express the answer here in terms of I cap and j cap notations. So Va vector will be what? I cap plus 3j cap meter per second, because it is 1. And similarly, what is the Vb vector? That is 3I cap meter per second. So the problem has been resolved. Actually, you can see the Vb has no tangential component and Vbn we have obtained what? 3 meter per second. Now what we have learned from this problem, let us practice in next problem. Example 2. A disk sliding with a velocity u on a frictionless horizontal floor strikes another identical disk kept at rest as shown in the figure. If coefficient of restitution is 0.5, find the velocities of the disk after the collision. So the situation is given like that. Now here angle are not given, but the geometry of situation will suggest how to find the angle between the line of collision and velocities. Actually, you can see here line of velocity vector is this and it is touching that disk. Now for this we just draw what will happen immediately before the collision. That geometry will help us to decide the necessary angle to find t and n components of u. The velocity components along the t and n axis immediately before and after the impact are shown. Just see, that is line of impact. Now you can see this angle we know to find component of u, when we can say it is r, that is r, that is r. So this hypotenuse is 2r and perpendicular is r. So sine theta is r upon 2r, or sine theta is half. So theta is 30 degrees. Geometry of the situation suggests that the angle between line of impact and line of velocity vector immediately before the collision or before the impact is 30 degrees. Theta is equal to sine inverse 1 by 2, that is 30 degrees. And with the help of that, we can find velocity components. And here we draw the diagram again, assuming theta to be 30 degrees. So this component will be u sine 30, uat, and the value of uat will be u by 2. And this component will be un, and value of un will be u cos 30, so u root 3 by 2. We can write here value. uat is u sine 30, so u by 2. And uan is u cos 30, so it will be root 3 by 2 into u. So these components we have shown immediately before the collision. Now what will happen about components along the t-axis? For t-axis, just see, this will be along this common tangent. So t component of disk A will remain same, u by 2. And t component of disk B also remains same. Previously it was 0, so after the collision it will be 0. The t components of velocities remain unchanged. Thus, t components of velocities after the collision, what they are? Vat is equal to uat, that is we have obtained this, again we are doing calculation u sine 30, that is half u. And vbt is equal to ubt, so vbt is 0. Now we show these in another diagram, what is immediately after the collision. The t and n components of velocities immediately before and after the collision are shown here. So that is t component, we have previously calculated u by 2, that is root 3 u by 2. And after the collision, this will remain u by 2 and there will be no t component. And n component we arbitrarily assumed in the same direction. So it will be easier to write momentum conservation equation and E equation. Now for n component, we treat the collision similar to an head-on collision. Component along the n-axis. For n components, the collision should be treated like a head-on collision. The momentum along the n-axis is conserved. So along the n-axis, what is the momentum after? mb vbn plus ma vn is equal to ma un plus mb into 0. So summation pix is equal to summation p final x. So what do we write here? mb vbn plus ma vn is equal to ma un plus mb ubn. And now we substitute the values. So what do you get here? mb vbn, m vbn plus m vn, m into u root 3 by 2 and plus m into 0, and cancelling out m throughout equation, what we can write? mbn plus vbn plus vn is equal to root 3 by 2u. Call it equation number 1. Coefficient of restitution E is defined as vbn minus vn is equal to E times uan minus ubn. Now substituting values, what we get? vbn minus vn is equal to root 3 by 4 u. Why? E was 0.5 and un was root 3 by 2. So 1 by 2 into root 3 by 2u, root 3 by 4u, and this was 0. So we have equation number 1 and 2, and by simultaneously solving equation 1 and 2, we can find the values of vbn and van. From equation 1 and 2, we get van is equal to root 3 by 8u and vbn to be 3 root 3 by 8u. And you can verify these calculations. Assuming the n and t axis as x and y axis, velocities of the disk after the collision can be written in vector form. What va is equal to root 3 by 8 I cap plus 1 by 2 j cap into u, and vb vector is equal to root 3 by 8 I cap into u. So in this way, we written the velocities as a vector component. Here what we assume? N to be x-axis and t to be the y-axis. Now let's discuss next example. In example 1 and 2, we have enough practice how we can analyze an head-on collision. Now let us see example 3. A ball of mass m strikes a stationary steel plate with a velocity u at an angle theta with a normal to the plate. As shown, mass M of the plate is infinitely larger than that of the ball small m. So m is much larger than small m. Denoting the coefficient of restitution by E, deduce expression for the velocity of the ball after the collision. So the situation is given here. The same situation we have taken in head-on collision, but here the same situation we take for oblique collision. Here the ball collides with a very heavy plate, making angle theta with the normal. Due to infinitely large mass, the finite impulse of the collision changes momentum and hence velocity of the plate by an insignificant amount. Therefore, the plate remains almost stationary. That is very important aspect. Actually, we know that total impulse of the deforming forces is finite, and that will be equal to change in momentum of the ball. And we know that the change in momentum of the ball is finite. So thus impulse is finite. And this finite impulse can change velocity of an infinitely heavy object by insignificant amount, because the momentum gained by the plate will be finite, and that finite momentum gained by infinite mass will be almost zero. That is common language. But what is actual thing? Actually, the momentum reduced by the ball will be momentum gained by the plate. And as masses of these two objects are having great difference, so change in velocities of these objects will have great difference. Change in velocity of the ball is finite, because finite momentum change upon finite mass. But for a plate, finite momentum change upon infinitely large mass. So its velocity change will be negligible as compared to that of the ball. So the plate will assumed, or can be assumed, fairly stationary, or can be assumed that its velocity is almost unchanged. Along the t-axis, the component of velocity of the ball remains unchanged, and along the n-axis, we can use momentum conservation and the idea of coefficient of restitution. The equation obtained from momentum conservation becomes unproductive due to infinitely large mass of the plate as compared to that of the ball and insignificant velocity acquired. Thus, we can use the idea of coefficient of restitution only. So here, momentum conservation we cannot use. So how we can find velocity of the ball after collision? For that n component, we use the coefficient of restitution, and for t component, we know that remains unchanged. Velocity of the ball immediately before, at the time of maximum deformation, and immediately after the collision are shown here in the figure. So here, that is the situation immediately before the collision. So it is ut, it is un, ut will be u sin theta and un will be u cos theta. At the time of maximum deformation, that normal component of velocity will be equal to that of the plate, so it will be almost zero. And this will be ut, so it will not change. Now, immediately after the collision, this is a velocity tangential component, it is velocity normal component, we assume it Vn, so it is a typing mistake. So let us call it Vn, so it will be Vt. Now we redraw the diagram again. So immediately before the collision, at the time of maximum deformation, immediately after the collision, please read it Vn. So component of a velocity of the ball along the t-axis, that remains unchanged. So Vt will be equal to ut. The t component of a velocity of the ball remain unchanged. So what we can write? Vt is equal to ut. So Vt is equal to ut or u sin theta. So that result we obtained. So you can write Vt is equal to ut. Component of a velocity of the ball along the n-axis. So please write it, it is Vn. So there is a typing mistake. So it is not Un, it is Vn. Now E is equal to Vmdn minus Vn upon Un minus Vmdn. What is Vmdn? Velocity of the ball at the time of maximum deformation. So this idea, and we know it is 0. Now substituting values, what we get? E is equal to 0 minus Vn, so it is Vn upon Un minus 0. So what we obtain? Vn is equal to EUN. It means velocity of the ball along normal component has reversed after collision with the stationary plate and become E time, just as we have seen in the case of head-on collision of a ball with a massive stationary plate. Thus, the end component of velocity of the ball is reversed in direction and becomes E times in magnitude. Velocity before the collision, U is equal to right here, ut t cap plus un n cap. So what will be velocity? Just we can have another notation. It will have a very important interpretation. Let us see. Or you can write u cos theta t cap plus u sin theta n cap. What is the velocity after the collision? V vector is ut t cap minus eun I cap. So it will be u cos theta t cap minus u sin theta n cap. Now, in this way, you can see that is another way of expressing velocities. We can relate the angle of incidence and angle of rebound. Angle of rebound is angle of velocity vector after collision from the common normal, and angle of incidence, angle of velocity vector from the common normal before the collision. Actually, here that is not strict, common normal is a line, so we are taking angle of line of velocity and common normal, and same is here. So what you can write, it is not very difficult, you can verify it. Cot phi is equal to E cot theta. That is not very difficult, just read it Vn and you can verify it. For perfectly elastic collision, what we got for perfectly elastic collision? V is equal to U, because this will be what? 1. Of course, direction of velocity change, but magnitude will remain same. And phi is equal to theta. E is 1, so cot phi is equal to cot theta, so phi is equal to theta. So it is similar to reflection of light. V is equal to ut t cap minus un n cap. Now we come on next example, example 4. Two parallel walls are 4 meters apart. A ball is projected from the foot of one of the walls such that in absence of the opposite wall, its range would have been 14 meters. After repeated collisions with the ball finally lands between the walls. Actually, just keep here. The ball finally lands between the wall. It means the height of walls are so large that the ball cannot cross them. And now, what we have to calculate? Part A. How will the maximum height reached and air time be affected from these collisions? So let's analyze it. What we know that tangential component in all the collisions will remain unchanged, and normal components will be reversed. And what are the collision type? After repeated collision with the walls, the ball finally lands between the walls. So type of collision is not given. Basically, it is perfectly elastic or not. But let us see. For this, it is required or not. Actually, we know that maximum height reached by a projectile and air time, both are decided by its vertical component of motion. And if you think the walls are vertical, so component of velocity is parallel to wall, means tangential component in any collision are vertical component and they are not going to change. So in any collision, vertical component of velocities, that is tangential for the collision, is not changing. It means vertical component of velocity remains unchanged due to collision. So these two quantities, maximum height reached and air time, will be unaffected. And for this, it is not required that whether the collision is elastic or what is the value of E. So let us document the solution. In a collision with any of the walls, the vertical component of velocity of the ball is the tangential component. So here this Vy is Vt and Vx is Vn. So at time we are assuming velocity V. So x and y we are taking this way. In a collision, the tangential component of a velocity remains unchanged. Thus, the vertical component of velocity of the ball remain unchanged in any of the collisions. So what we can write from here? The maximum height reached and the air time, both of a projectile depend on the vertical component of motion, and that is being unaltered by these collisions. So what we can say? Since the vertical component of motion of the ball remains unaffected by the collisions with the walls, the maximum height and the air time both will remain unchanged. So that is very remarkable. Now we can see what is asked in part B. Find the total number of collisions with the walls before the ball hits the ground and where the ball finally hit the ground. Here we have to assume that is E to be 1. It is not mentioned, so but we assume collision to be perfectly elastic. Solution. Consider a perfectly elastic collision with a wall. Actually, here the collision was not mentioned, so it is an open problem. So for different value of E, the result will be different, but that situation we are solving for E is equal to 1. So we are considering perfectly elastic collision with a wall. What will happen in perfect elastic collision? At what angle the ball will come, the same angle the ball will go with the same speed. So this Vt will remain the same, and this component will be reversed, but magnitude will remain the same. That is situation immediately before the collision, that is situation immediately after the collision. You can see here Vy is equal to Vt tangential, so it will remain Vy. It is Vx, it is normal component, so it will remain Vx in magnitude but reverse in direction. A perfectly elastic collision of a ball with a fixed wall can be considered like reflection of light of a light ray. And this is a very remarkable idea. We can use it. Thus, it can be assumed that after every collision, path of the projectile is flipped horizontally. So, it was flipped horizontally, it means it is flipped about the and vertical axis passing through the point of collision. The above idea suggests us to correlate the path of the ball between the walls with its trajectory if the walls were not present, as shown in the figure. Actually, you can see here, that is first wall. From here the ball was projected, and there is second wall 4 meters apart. So this ball will go here, collide, go here, collide and come here. So we assume there are 3 collisions, but how we assume 3 collisions, it will explain by this time. So this is the trajectory what we are assuming without or in the absence of this wall. So the C will mark lines of 4 meters apart. So actually what happens, the ball collide here, and the trajectory from here to here, what it would have been, it is flipped. So that you can see that segment has been flipped here. Now, but this segment will remain. Actually, after that, the ball would have gone here if this wall were not present. But here again trajectory will flip. So it is third collision, and here again trajectory will flip. So what is, you can see that remaining distance is 2 meters, 4 meters, 4 meters, 4 meters, and the total distance is 40. So up to here to it is 12, so it will be 2. So the ball will land on the ground 2 meters away from opposite wall, or the distance is 4 meters, so 2 meters from either the wall, or you can say in between at the middle point between the walls. Thus, total number of collisions, you can write they are 3, with the walls are 3, and the ball will land midway between the walls. That is a very simple idea. Actually, how we have made the concept of reflection here. Now, what the idea we have learned here, just we try to extend it to some other example. Let us see. Example 5. A ball projected from the ground makes a head-on collision with a wall, then after one bounce hits the point of projection. If coefficient of restitution for all the collisions are equal, find the coefficient of restitution. Actually, what is given here, that is a ball projected from the ground makes a head-on collision with the wall. It means when the ball is colliding with the wall, it is head-on. It means velocity of the ball must be along the common normal, means horizontal. So this first collision is taking place at the highest point of the trajectory. That we have to extract from here. The possible path of the ball is, now let us estimate the possible path. So what we have assumed, that the first collision will be at the highest point. So let us assume the ground and its wall, x and y axis. So that is velocity projection, x component, y component. So that is here, first collision at the highest point. Now what will happen at this collision? The x component velocity, which was ux, will not change from here to here. But after the collision, the x component is a normal component, so it will get reversed and becomes e times. So the ball will start moving, but it will not reach here, it will fall here. So here it will again bounce and come here. So that is first collision, second collision with the ground, and in the third collision is at the point of projection. So that is the path we can estimate from the given information. Now collision with the wall. Actually, we analyze the collision with the wall. Vertical component of velocity, being the tangential component, remains unchanged. 0 at the top. So it was 0, so after collision it will remain 0. So there is only horizontal component, that is normal component, and I have just explained you, it will becomes reverse in direction and e times in magnitude. Horizontal component of velocity, being the normal component, become reverse in direction and e times in magnitude. So we can show here, that is the ux before collision, and after collision it will become EUX. So ball will come here, and as it falls, this component horizontal will not change. So here the ball will collide with EUX. And again, we know that earlier vertical component of velocity was 0. So when the ball will land here, the vertical component will be UI, but in downward direction. Collision with the ground. So when the ball is about to collide with the ground, or immediately before the collision with the ground, we know both the components of velocity. Horizontal component is towards left, it is UX, and vertical component is downward, that is UI. Horizontal component of velocity, being the tangential component for the collision with the ground, remains unchanged. So here this component will remain unchanged after the collision. But vertical component of velocity, here is the normal component, so it will become reversed and e times. So before collision it was UI, so after collision it will become EUI. Vertical component of a velocity, being the normal component, becomes reversed in direction and e times in magnitude. So we will show here, that is immediately before the collision, and that is immediately after the collision. So we have shown what will happen in this collision, and we are not supposed to analyze this collision, what will happen here, because that is, of course the ball will bounce here, but we have to analyze event up to this instant of time. Time of flight on different paths, a segment. Actually there are 3 path segments, this, and this. Let us denote time of flight from here, T1, for this T2, and for this entire T3. Now write time of flight expression. Actually, you know, T1 is UI upon G, that is very simple, from the null is the projectile motion you can write. T1 is UI by G. And T2 is also UI by G. Because initial and final particular velocities are equal. So T1 and T2 are equal. But what about T3? That will be 2 EUY by G. T3 is 2 EUY by G. So time of flight for entire projectile path is twice of vertical component of velocity projection upon G. So we have to do it. Now we have obtained how much time the ball will take on different segments of path. But we can note here a very remarkable idea. What? the leftward horizontal displacement, that is from here to here, is equal to its rightward horizontal displacement. And we will make use of this idea. So we have again reproduced the diagram. What we can write here, we will again write the values what we obtained. T1 is ui by g, T2 is also ui by g, and T3 is 2euy by g. And what idea just I have explained you, that the rightward horizontal displacement of the ball is equal to leftward horizontal displacement. That is apparent here. The ball travels equal horizontal distance in the leftward and rightward directions. Thus, what is this distance? You can write here ux into t1. This for leftward. So ux into t1. For rightward, it is eux into t2 and eux into t3. So actually from here to here, the x component velocity remains same, and total time is t1 plus t2 plus t3. So we can write in this way. Now we substitute values of t1, t2 and t3 in this equation. Substituting expressions for t1, t2 and t3, we get ux into uy by g is equal toeux into uy by g pluseux into 2euy by g. And now we can see from the entire equation, ux uy by g we can cancel out. So what we get here, 1, here e, here 2e square. So here get 1 is equal to e plus 2e square. Now it is a quadratic equation, we can find its roots. Roots of the quadratic equation are e is equal to -1 and e is equal to half. Actually, for a physical collision, value of e ranges from 0 to 1, so this value is unacceptable. So that is the value of coefficient of restitution for these collisions. Coefficient of restitution lies in the range close interval 0 to 1. Thus, for the given situation, a is equal to half. So that is a very interesting situation. Now, again you can see this problem is not difficult. Only we have to change. We must be expert enough in taking the decision what is happening with the t component, what is happening with the n component, and which one is the t component, which one is the n component. Because just see here, for the ball, the horizontal velocity which is n component, but for the ground it will become t component. So if you will not get confused in this interchange of t and n component thinking, the problem is quite simple. Oblique collision, when one colliding body is constrained in its motion. That is again very important or very interesting variety problem. Actually, till so far, what we assume in all the collisions, the bodies are free to move, or you can say there are no impulsive external forces on the bodies. But here, there are such impulsive external force on one of the body that this body is constrained to move in a particular way. This we can understand with the help of examples. Consider the following situations. Here, there is a wedge. The wedge was moving with velocity uv, and the ball hit here the wedge with velocity uv. Now you can see, before and after the collision, the ball is free to move, but this wedge can move only in horizontal direction, so it is constrained to move only in horizontal direction. Collision between the ball A, free to move in any direction, and the wedge B, which is constrained to move on the horizontal floor. So that is what situation? We can think another situation here. This ball B was hanging from the ceiling with a thread, and this ball A falls and strikes here. So the ball A has the same situation as in this case, but the ball B can move only on circular path. So the ball B is constrained because of external impulsive tension in the thread, and here this wedge was constrained because of external impulsive normal direction from the ground. Collision between the ball A, free to move in any direction, and the ball B, which is constrained to move on a circular path. So these are the situations which are enough to understand what kind of problem we are going to discuss in this article. In these situations, we have to find three unknowns that are magnitude and direction of the velocity of the ball A after the collision and magnitude of velocity of the body B. So we need three equations. Two equations we can write. First from the continuity of tangential component of the velocity of the ball A, and second from the conservation of the momentum in the horizontal direction. The only thing to decide how can we write the equation for coefficient of restitution in head-on collision and oblique collision, where we have developed the equation of a coefficient of a restitution. There were no external impulses along the line of impact, but here component of external impulse are present along the line of impact. In the first case, it is the component of the impulse from the normal direction from the ground, and in the second case, it is that of the tensile force of the string. So that is a complete description of the idea. Actually, what we do in both the situations, you can see in what direction ball A will move after the collision is unknown, and its magnitude is also unknown. So regarding ball A, we have two unknown to decide. The magnitude means speed immediately after collision and direction. But the body B, here the weight or the body which is constant to move, its direction of motion is known. So its magnitude we have decided only. So we have to make three equations. Again, it is impulsive element, so we cannot make use of Newton's laws and work energy. So what we can do here? Actually, one equation we can write from the continuity of tangential component of ball A, because during the collision, the interaction force between ball A and body B are along the normal. So there is no friction. We have mentioned earlier that in collision, friction has to be ignored until it is specifically stated to be considered. So here what we do, and the tangential component of ball A will remain unchanged. So that is one result. You can see it is one equation, or you can say one result. Now we have to write two independent equations. Now in both the situations, you can see there are no external horizontal forces. So in horizontal direction, total momentum of the system will remain conserved. So we are sure about that equation. And third equation, how we can write equation for coefficient of restitution. Actually, when we have developed that idea, what we assumed that there are no external impulses on any of the colliding bodies. I am saying external impulses means external impulses comparable to the impulses of deforming forces. But here, the external impulses of tensile force and normal direction are comparable because they are restraining the body to move in some other direction. So, can we use the same relation here? Now, the question is we have to explore that idea, and that is very interesting. We will resolve this difficulty with the help of the first case, that is collision between the ball and the wedge. So we will take this one, and with the help of this, we will resolve the difficulty. What? How can we write coefficient of E equation if external impulses are present during the collision? Oblique collision between the ball A and the wedge B, which is constant to move on a frictionless horizontal floor. That is, we are again describing the situation. Here, immediately before collision, the velocity of ball was UA and the velocity of wedge was UB. And immediately after collision, we assume the velocity of ball to be in this direction V. You can see the direction is slightly different, and velocity of wedge will become VB. So here resolve T and N component. Here N component. Actually, there is no need to write T component of velocity of wedge because T component of velocity of wedge is going to change. It is T component of velocity of ball which remain continuous, or it will not change. So we resolve this here. But for N component we need just to write coefficient of restitution. Here we resolve this VAT and VAN. Similarly, VBN. And now we resolve this x and y axis. So since there is no friction, the component of momentum and hence velocity of the ball along the t-axis remains unchanged. So what we can write here? VAT is equal to UAT. So VAT is equal to UAT. That we can say equation 1, or it is a direct result. Since there is no external forces in the horizontal direction, the component of the total momentum in the horizontal direction remains conserved. So we write total momentum horizontal component to be conserved. So what it was before the collision, the same it will be after the collision. So mvb plus mvx is equal to small mvx plus capital MUV. Let us try to understand. This capital M into VB is the horizontal component, and for this, what we write? Small m into Vx, the x component of velocity of A. This. And before the collision, small m into Ux, x component of velocity of A, and capital M into UV. So that is what equation number 2, that is the equation of conservation of momentum in horizontal direction. To know how will the expression of E be modified, we make use of the impulse momentum principle. Actually, E was derived with the help of impulse momentum principle. So here how E will be modified, or it will not be modified. We don't know whether it will be modified or not. That can only be explored with the help of impulse momentum principle along the axis. At the time of maximum deformation and components of velocities of both the bodies must be equal, denoting velocity of the wedge by U at the time of maximum deformation and component of velocity of both the bodies are shown here in this diagram. You can see. This we assume U, velocity of U at the time of velocity of wedge is U at the time of maximum deformation, and that is N component. Similarly, the tangential component of disk is not going to change, so it will remain VUN, and that is what the normal component will be equal. They will be equal. Of course, in the diagram we have shown unequal, but they must be equal because at the time of maximum deformation, the normal component of velocity of both the bodies must be equal. It is a very common fact. So this was the detail. Now we redraw all these three diagrams and try to apply impulse momentum principle as we had done in case of head-on collision. Denoting impulses of the mutual forces at the point of contact during deformation and restitution by JD and JR, we write impulse momentum equations for the ball along the n-axis and for the wedge in the horizontal direction. Why we are not writing for the wedge along the n-axis? Because the impulse of the normal direction from the ground is unknown. But if you write along the horizontal axis, that will have no contribution. So that is immediately before the collision, we have shown velocity UAT, UN, and that velocity was UA, and UB, and this component is UN. At the time of maximum deformation, this velocity has a U, so it is UN, it is UN. We are interested only in these two. So immediately after the collision, the velocity of ball has been assumed VA, so it will be VAT. So VAT is equal to UAT, of course, from the continuity of the tangential component, and this component we are assuming VN, and this velocity we are assuming VB, so it will be VBN. Impulse momentum equation for the ball along the n-axis for the period of deformation of the ball. So what will be? MUN minus JD is equal to MUN. MAUN minus JD is equal to MAUN. This is equation number 1. For the period of restitution of the ball, what will it be? MUN minus J of R is equal to MVN. MUN UN minus J of R is equal to MAVN. Equation number 2. Impulse momentum equation for the wedge in a horizontal direction. Let us write. For horizontal, what we can say? For the period of deformation, let us think what it will be. Actually, in horizontal direction, we have to consider the horizontal component of impulse of deforming forces during deformation period. Actually, you can see that will act in this direction. Now you can see this, and from vertical this angle is theta, so from horizontal this angle will be 90 minus theta. So that component will be what? JD or JR cos 90 minus theta, it means sin theta. So MB UB plus JD sin theta is equal to MBU. This. Now I will again explain. In horizontal direction, component of JD will be JD sin theta. Why? That is, JD will be in this direction. So from vertical angle is theta, and from horizontal will be 90 minus theta. So horizontal component will be what? JD cos 90 minus theta, JD sin theta. This way. In similar fashion, we write for the period of restitution. For the period of restitution, for the wedge, what will be? MBU plus JR sin theta is equal to MBVB. MBU plus JR sin theta is equal to MBVB. Equation number 4. Now we will rewrite all these 4 equations and try to reduce coefficient of restitution as we have done in head-on collision. From equation 1 to equation 4, for reference, we write here for the ball MAUN minus JD MAUN. Equation first, MAUN minus JR is equal to MAVN. Equation second, for the wedge, MBUB plus JD sin theta is equal to MBU. Equation third, MBU plus JR sin theta is equal to MBVB. Equation fourth. So this equation we have written just for reference. We have deduced them previously. Now what we do? From equation 1 and 2, the expression for E for the ball, the same thing we have done while we have developed the expression for coefficient of restitution in head-on collision. So E will be JR by JD. So JR we can find from this equation and JD from this equation, and after substituting values, what we get? UN minus VAN upon UN minus UN. How you can see? JD will be M into UN minus this UN. So it will be denominator, and similarly for here, GR will be MUN minus VAN. So here MAN and ML cancel. So we can call this equation to be fifth equation. From equation third and fourth, expression of E for the wedge. So what will E is equal to JR upon JD. So it will be JR sin theta upon JD sin theta. Sin theta and sin theta will cancel out. So what we have here? VB minus U upon U minus UB. So there is no need, you can verify it, very simple idea. So multiplying the numerator and denominator by sin theta again, we get velocity components along the n-axis. How? See this diagram. Actually, here this angle is theta. So if we multiply VBN with sin theta, so what we get? Just see. Multiplying numerator and denominator by sin theta, this is here VB. So if you multiply VB by sin theta, you get this. So VBN. Similarly, if you multiply U was also aligned, sin theta, you will get the n component. So if these velocities are again multiplied by sin theta, we will get what? N components. So, and multiplying the numerator and denominator by sin theta will not alter the value of E. So what I write here? E is equal to JR by JD is equal to VB sin theta minus U sin theta upon U sin theta minus UB sin theta. So what is VBN? It is UN. It is UN minus UBN. So VBN minus UN upon UN minus VBN. We can call this equation number 6. Now see equation 5th as 6. So both the coefficient of restitution must be equal because this JR and JD, this JR and this actually they are action reaction pairs. So JR here and JR here are action reactions, so they must be equal. JD here and JD here are action reactions, so they must be equal. So both the E must be equal. So let us equate them. From equation fifth, and that is what actually here it should be 6. There is typing error. Read 6. What we get E is equal to VBN minus VN and UN minus VB. The same thing we will do. What we equate these two and add numerators to numerator and denominator to denominator. We will have same ratio and get this result. Now you can see it is the same result what we have. What we are using in oblique collision of unconstrained bodies. So very surprising. It means external impulse were present along the line of impact, but they are not altering the expression for coefficient of restitution. So that is very surprising result. Again, this result cannot be cannot be explained with some other ideas. We have to follow such calculations. We can call this equation number 3. So now we have 3 equations. What? First, continuity of tangential component of the velocity of the ball. Second, conservation of linear momentum in a horizontal direction. And third, coefficient of restitution for the velocities along the common normal. So by these 3 equations we can identify all the 3 unknowns. The situation at hand can be analyzed with the help of equation 1, 2 and 3. We are again rewriting equation. VAT is equal to UAT, continuity of velocity tangential component of the ball. Equation 1. Equation 2, momentum conservation horizontal direction. MVB plus small m Vx is equal to small m Ux plus m Ub. Momentum x component after the collision, momentum x component before the collision, and coefficient of restitution. Third equation we again rewrite it is equal to VBN minus VAN upon UN minus UB. Actually, this was it is a UBN. Just please make it correction here. Actually, this is what UBN. So there is starting error, small time error. Just please take care of. It will be UBN. So here it will be UBN. It should be UBN. So now with the help of these 3 equations, we can analyze this situation. The general strategy to analyze such situations. If one of the bodies undergoing collision is free to move and the other one is constrained to move in a particular direction in which there is no external force, impulsive force, we can use a general strategy based on the 3 equations deduced. What? First, the t component of velocity of the body free to move remains unchanged. VAT is equal to UAT. Equation number 1. Second, no external forces act in the direction where the constrained body is free to move. The total momentum of the system in this direction remains conserved. Please take care, this direction will not be always horizontal. Denoting this direction to be the x direction we can write. Actually, just see here, the direction where the constrained body is free to move. Actually, in both the situations, what we have taken, that direction was x. So it may be some other direction. So let us denote that direction by x. So in this direction, we will write conservation momentum. MVBx plus small m Vx is equal to small m Ux plus capital M Vbx. Third, expression for the coefficient of restitution is valid for the velocity components of the bodies along the line of impact, that is the common normal. So what we write here is equal to VBN minus VAN upon UN minus UBN. So just again, please see it is UBN. So that is equation number 3. Now, just after developing this idea, we try to exploit it in analyzing some problem. Say example 7. A 250-gram ball moving horizontally with a velocity 10.0 meter per second strikes an inclined face of a 720-gram frictionless pitch as shown in the figure. the wedge is placed at rest on a frictionless horizontal floor. If the coefficient of restitution is 0.8, calculate velocity of the wedge after the impact. Situation was given. So what we have developed here theory, that is here, for simplicity, the velocity of wedge has been assumed 0 and velocity of ball is here and angle 37 just to make calculation similar. So how we proceed? So that is what we consider the N and T component of the ball before collision and after collision. T component will remain same and N component will assume. Similarly, after the collision, velocity of the wedge will assumes say V and its N component will show. Distinguishing the ball and the wedge by subscripts 1 and 2. Conditions immediately before and after the collision are shown here. So U1 before the collision. So T and N components will resolve. So this will be angle sin 37. So what will be this N component? U11 and this T component U1T. So you can write here U1 sin 37, this is U1 cos 37. X and Y axis. And after the collision, let us assume V1 in this direction and V2 in this direction. V1 for the ball and V2 for the wedge. So again we draw the components. So this here V1T and V1N and N component of V2. So no need to show the T component. So here the N component of V2 is V2N. So we can show here V2N. Now we have shown all the components relevant. So here we know that tangential component will remain same. So let us first deduce their values. The T component of a velocity of the body free to move remain unchanged. So what we can write here? V1T is equal to U1T, or U1T is what? U1 cos 37. So that is 10 into cos 37. So how much it is? 8 meter per second. So this velocity is 8, so it will remain 8. So V1T is 8 meter per second. We have obtained it. So equation number 1 or result number 1. Due to absence of external forces in the horizontal direction, the total horizontal component of the momentum is conserved. So how we can write here? Small m into U1, U1 was given 10 and ball was 250 grams. So this mass into this velocity. And here this is 0. And now we write how we can write after component. So Pix is equal to P final x. What? M1 U1 is equal to M1. V1T cos 37 plus V1N cos 53 plus M2 V2. Let us understand it. It is initial momentum that was only with the ball. So M1 U1. Now X component of momentum of the ball M1 of mass M1 after the collision. So we are not knowing this. We know this component and we have to determine this component. So horizontal component momentum will write in terms of this component. So this angle 37. So from horizontal this make 37. This will make 53. So what we write? V1T cos 37 and V1N cos 53. And for the wedge it is capital M into V2. So just understand it. Now we substitute the values. So 0.25 into 10 is equal to 0.25 into 8 into 4.5 plus 3V1N upon 5 plus 0.72 into V2, because cos 37 is 4 by 5 and cos 53 is 3 by 5. And this we have obtained 8. So we substitute it here. So what equation we get? 0.18 V2 plus 3V1N upon 5 is equal to 3.6. It is called equation number 2. Now we have to implement the third idea, writing equation from expression of coefficient of restitution. So let us see. Coefficient of restitution, that is velocity immediately before collision. We again read of the diagram just to reference. So that is U1, that is the U1N and U1T. This V1, this is what V1t and V1n, and this is what? This component is V2n. So we know that the coefficient of restitution is valid even in this case for the normal component of velocities. So just write it. E is equal to VBN minus VAN upon UN minus UBN. Now that is general expression. We substitute value. B will be replaced by 2 and A will be replaced by 1. So E was given 0.8, VBN this V2 sine 37, and this is a known V1n, and this is what UN, that is U1 sine 37 minus 0. And from this equation what we obtain, 3V2 by 5 minus V1n is equal to 4.8. Now if you see equation 2 and 3, they are involving V2 and V1n. So both these values we can determine from equation 2 and 3. From equation 2 and 3, we get V2 is equal to 2 meter per second. That was required answer. Now we have seen that in oblique collision, it is nothing special. Actually, oblique collision is analyzed along T component and along N components, or along T axis, along N axis. Along T axis, the bodies which are free to move, their momenta and velocities will remain unchanged. And along N axis, the collisions should be treated or must be treated similar to an head-on collision. And in the last type of variety, when one of the body is constant, what we have seen, we can have three ideas. The body which is free to move before and after the collision, T component of that body will remain unchanged. And there is constant body, and identify the direction in which the constant body is free to move. In that direction, total momentum of the system will remain conserved. And third is very striking idea that the coefficient of restitution is still valid for the normal component of velocity. By using this idea, we can apply and do similar problem as we have done here. Now it concludes today's talk. Thanks for patient listening. For the next lecture, now it is time to conclude today's talk. Thanks for patient listening. We will meet in the next lecture. In the next lecture, we discuss about center of mass or mass center. Thanks. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.